In this video, we are going to present you our work, Structure Aggregation for Cross-Spectral Stereo Image Guided Denoising. To begin with, let's suppose we are taking a photo in a low-light environment. The captured images are inevitably corrupted by random noise, especially in a short exposure time. Although current single-image denoisers can basically remove the noise completely, they cannot avoid over-smoothing the image details. But if we can capture an extra clean image, which is usually from a different spectral band like near-infrared, it can be used to guide the denoising process for better structure reconstruction. Previous studies on guided denoising basically require the input images to be well aligned. However, considering the application in portable devices such as smartphones, a more practical way is to use a stereo camera system, but the input images will have disparities. To exploit the unaligned guidance information in this work, we propose a novel two-stage guided denoising framework. Before elaborating our work, let's first revisit the classic guided filtering theory. Given a pair of noisy target image and a guidance image, the clean target image can be estimated using a spatially variant linear representation model of the guidance image. In addition, if the guidance image contains richer textures, they can also be transferred to the filtering result. This linear representation model is simple and effective, but it requires the input images to be structurally consistent. For image restoration tasks, if there are unique structures in the guidance image, the inconsistent contents can lead to ghosting artifacts. In other words, the weight, A, only has the function of structure transfer, but struggles to judge whether the transfer is appropriate. For stereo camera systems, the structural inconsistency issue arises from the misalignment of images. Therefore, one straightforward solution is to register the input image pairs using stereo matching techniques. However, it's quite challenging to obtain accurate disparity estimation in the case of noise contamination, not to mention that the paired images can have different modalities. Obtaining a large number of ground truth disparities for supervised training is also a quite heavy work. Now, let's review our original purpose. Since our real purpose is to obtain two structurally aligned images, do we still need to obey the one-to-one correspondence policy in stereo matching? For each target pixel, stereo matching aims to find one corresponding pixel from the other view among the candidates restricted by the maximum disparity. Due to the structural redundancy of natural images, some candidates can be quite similar to each other. So, why don't we aggregate all of them based on their correlation to the target pixel instead of just picking out only one winner? Motivated by this, we propose that each target pixel can be estimated by a linear representation of all candidate pixels in the guidance image within the range of the maximum disparity, which can be regarded as a process of aggregating the non-local information. Further, to enable the aggregation process to focus more on structural correspondence than structure intensities, we split the weight into two parts, a perceptual weight and a scale weight. The perceptual weight aims to regress the target structures and generate the structure map, which we also refer to as a structure aggregator. The scale weight is used to adjust the structural intensity to match the target image. So, our guided denoising process can be divided into two stages. We design a convolutional neural network, called as SANet, to accomplish the entire denoising process. In the structure aggregation stage, we aggregate non-local information from the guidance image to generate a structure map that is structurally aligned with the target image. In the actual implementation, we circularly translate the guidance image in the horizontal direction, and then stack the original and the translated guidance images together in the channel direction. In this manner, the aggregation process can be achieved by weighted averaging these translated guidance images. Here is the network architecture of our structure aggregation module. First, two identical encoders extract two feature maps from the input images, respectively. To evaluate the feature-wise correlation between the target and the guidance images within the range of the maximum disparity, we circularly shift the feature map of the guidance image to compute the channel-wise cross-correlation with the target one. Then, the correlation map is fed into a decoder to compute the perceptual weight before computing the structure map. The structure aggregation module is trained by minimizing the perceptual difference between the ground truth target and the estimated structure map. Compared to cross-modal stereo matching methods such as the DASC-based one, our structure aggregation strategy shows high robustness to noise. Now, let's take a look at the aggregation process. As the guidance image is shifted, the structure map is gradually completed. Finally, voila! We obtain our desired structure map. In the guided denoising stage, we regress the final denoising result based on the estimated structure map. The design of the guided denoising module is actually quite flexible. In this work, we use FGDNet as the backbone network with slight adjustments to accomplish this task. That is, the linear representation is learned in the frequency domain, and a noise map is also estimated to improve the robustness of guided denoising under different noise levels. In the training stage, our guided denoising module is optimized using the smooth L1 loss function. To demonstrate the effectiveness of this framework, we evaluate our model under Poisson and Gaussian noise on 3 datasets including an RGB NIR1 and 2 synthetic cross-spectral ones. We use PSNR, SSIM and LPIPS for quantitative evaluation. For the RGB-only stereo datasets, we switch the channel order of the right view images to simulate the cross-spectral cases. The network processes only one channel at a time. Here, we can observe that our model achieves the highest accuracy on all 3 metrics. Visual comparisons show that our guided denoising method can effectively restore salient structures according to the unaligned guidance information. Also, the denoising accuracy decreases when any component of the network is deactivated. Compared to other unsupervised cross-modal stereo matching methods, it's our structure aggregation strategy that enables the guided denoiser to deal with unaligned situations. Besides, this aggregation strategy can also benefit other guided denoisers that are originally designed for aligned image pairs. In addition to guided denoising, in fact, our structure aggregation strategy can be also applied to other guided restoration tasks including guided super-resolution and guided deblurring, and thus has the potential to handle a wider range of application scenarios. In a word, in this work, we explore the guided denoising model in the unaligned situation and introduce a noise-robust structure aggregation strategy to take the advantage of the unaligned guidance information, which definitely improves the applicability of guided denoising in practical applications.